Hello everyone and welcome to the class of Materials and Their Properties from the Federal University of ABC. I'm Professor Mathilde Champeau from Material Engineering course, and today we are going to focus on the atomic structure and interatomic bonding. So before starting to speak about materials. So first of all, we are going to remember basic concepts of the atomic structure, of the Bohr's atomic structure, and that of quantum mechanics and electronegativity. And after that, we are going to see the different kind of interatomic bonding that exists, the bonding energy, and we will introduce some relationship between some properties and the kind of interatomic bonding found in materials. So first of all, let's focus on the atom. So each atom consists of a nucleus that contains two particles, protons and neutrons. And around this nucleus, electrons are moving. So let's remember that an atom is neutral, and so in a neutral atom, we have the same amount of electrons and protons. So electrons and protons are electrically charged. The electrons have a negative charge and the protons have a positive charge. The charge magnitude of them is 1.6 × 10⁻19 coulomb, whereas the neutrons are electrically neutral. So the masses of these subatomic particles are really small. The protons and neutrons have approximately the same mass, 1.67 × 10⁻27 kilograms, and the electrons have a lower mass, 9.11 10⁻31 kilograms. Each chemical element is characterized by two values. The first one is the atomic number. We write it Z. It is the number of protons in the nucleus. The other parameter is the atomic mass, A, which is the sum of masses of the protons and neutrons within the nucleus. And let's remember that the equivalence of 1 mole, so 1 mole of substance contains 6.023 10⁻23 atoms, which is the Avogadro's number that is really useful for some calculations. So let's focus on this atomic model and more specifically on electrons that are involved in the interatomic bonding. So let's focus on electrons. So in order to understand the behavior of electrons in atoms, and in order to explain many phenomena that involve electrons in solids, it was noticed last century that it was not able to explain some of these phenomena using classical mechanics. So this was followed by the necessity and the establishment of a set of principles and laws that govern the systems of atomic and subatomic entities that is known as quantum mechanic concepts. So let's introduce these quantum mechanic concepts in order to understand these phenomenon and behaviors involved in interatomic bondings. So let's come back to the Bohr's atomic model. So if you remember, the Bohr's atomic model said that we have the nucleus right here that is represented in orange. And around it, we have the electrons that revolve around the nucleus, but they revolve in discrete orbital, in discrete position. And this energy of each orbital have one specific value, okay? And the energies of the electrons are quantized, which means that the energy of these electrons have only specific values which are associated to the energy level, energy states. So either I represent this configuration for my atom with the nucleus and the electrons that evolve around it at specific position, specific distance from this nucleus. Either I can also represent the energy level for these different orbitals as a representation at the right of the slide. So as you can see, on this representation, we have the energy increasing from the top to from the bottom to the top. And we represent the different atomic level, atomic shell. And as you can see, there is a number given attributed to each atomic shell, n. So we start from the lower, the orbital with lower energy, which is the closest to the nucleus, that is written n equal 1. After we have the second orbital, which is written n equal 2, and so on. And each of these orbitals have a specific energy value. And so electron may change from one orbital to another only if they absorb energy of specific value. So if here I have an electron that is not represented, but this electron right here, we could also represent it on this energy level, energy state. For this electron to go to an orbital of a higher energy value, so I need to give him, to give it some energy. And the energy I have to give him must be equal to the difference of energy between this level and the first one, the initial one, okay? So only this specific energy value will enable the electron to shift and to go to another orbital, okay? So how can I give this energy to the electron? It can be electric energy, it can be thermal energy, but it can be also a specific photon or light of a specific energy value that will promote this transition from one energy level to another one, okay? And on the contrary, we can have an electron from an outer orbital that can shift to a lower energy level orbital. And in that case, so the electron will lose energy. But the Bohr model has some limitation and cannot explain various phenomena. So it has been introduced a wave mechanical model in order to be able to explain this phenomena. So what is this wave mechanical model? So in fact, it considers that electrons behave both as a particle and as a wave. So in the Bohr model, we consider the electron as a particle. So we said that the electron is in a discrete orbital at a specific distance from the nucleus. It has a specific energy. And when we will consider this new model, we will also consider that, in fact, the position of this electron corresponds to a probability of location around the nucleus, okay? So, in fact, instead of representing like this, that the electron is in a discrete orbital, so we will consider that we will consider the probability of location around the nucleus as it is represented on this figure. So as you can see, of course, the position predicted by the Bohr model is the one that will have the higher probability where we can find this electron. But so this wave mechanical model is a little bit more complex than the Bohr atomic model. So we will explain the behaviors of atoms and materials using one model or another in this course. Either we will consider that it behaves as a particle, or we consider that the atoms behave, and the electrons in the atoms behave as a wave. So depending on which model enable me to explain more easily the phenomenon, so I will select one model or another. Okay. So in this wave mechanical model that we have introduced, we also need to introduce that every electron in an atom is characterized by 4 quantum numbers in order to be able to define what will be the energy of our electron. So let's introduce these 4 quantum numbers. So first of all, let's remember that in an atom, we won't find 2 electrons with the same quantum numbers. They will have distinct quantum numbers. So the first quantum number that we will call the principal quantum number, n, specifies a shell where we will find our electron. So maybe you remember this notation right here, n, which was introduced when we present the Bohr model right here, n equal 1, 1 equal 2, n equal 3, that corresponded to the orbital. So it specifies the energy level and the orbital size, okay, in this model. So n has integral value started from 1, so 1, 2, 3, 4, 5, and so on. And in some specific situation, we will also use this letter, capital letter, K, L, M, N, O, and so on, but it is the same meaning. Then we have the second quantum number, or orbital quantum number, that we will write L, that describe the subshell or the shape of this electron subshell. Okay, so the value of L will depend on the principal quantum number n. So the value for L will be n-1 or 0, 1, 2, 3, 4, depending on the principal quantum number. So you will find mainly the representation, the notation for this subshell as S, P, G, F. So as you can see, it is represented on this figure for the wave mechanical model. So see, if I make the equivalence between the Bohr model and the wave mechanical model, so instead of represented in the Bohr model n, the orbital with the quantum number n equal 1. In the wave mechanical model, I will write it 1s. So 1 corresponds to the principal quantum number n, and s corresponds to the orbital quantum number. Okay. If I have a look to the second orbital, so as you can see, when n equal 2, so we have 2 orbital quantum number or 2 subshells, which are 2s and 2p. And for the principal quantum number n, or the shell n equals 3, so I have 3 orbital quantum number L, 3 subshells, 3s, 3p, and 3d. Okay. Okay, so we introduce a principal quantum number, which specifies a shell, and the orbital quantum number that specifies a subshell. So now let's introduce the third one, which is a magnetic orbital quantum number, which is written M with the subscript L. So ML will take a specific value depending on the orbital quantum number L. So minus L plus 1, L minus 1, L, and so on. So depending on the orbital quantum number, we will know the magnetic orbital quantum number that can take or that can describe our electron. So what is the meaning of this magnetic orbital quantum number? In fact, it indicates the orbital orientation. And so we can maybe have a look directly to this slide. So on the figure, you can see that for the case of the orbital S, L equal to 0. So there is only this orientation. I mean, for the orbital. So then, if we go to the case that we have a p subshell, we will have three different orientation. Okay, so p equal correspond to 1, the number 1. So in fact, you will have minus 1, 0, and 1, which means we have 3 orientation value in that case. And you can see that if I represent 3 axes to represent the space, so I will be able to represent 3 orbital orientation around each axis. Okay, so this is in the case of the p subshell, and in the case of the d subshell, you can see that it becomes we have more variety of orbital orientation, and we have 5 different possible orientation for this orbital, for this subshell. And so the last quantum number is the spin number or spin moment. It is written ms, and it can take only 2 values, plus 1/2 and minus 1/2, and it will represent, in fact, the orientation of the spin of the electron. Okay, so the spin of the electron can orientate up, plus 1/2, or it can be orientated down, minus 1/2. Okay, so it is the direction of the spin. So we described the 4 quantum numbers, and here in this table, so you can find a summary of what we explained. So depending on the principal quantum number and the value of this quantum number, so we find specific sublevels or subshells. It corresponds to, or we have a number of orbitals. So for a subshell S, we have only 1 shape of orbital. For P, we have 3 orientation for this orbital. D, we have 5, and F, 7. So the number of orbitals that we will find in each shell will depend, can be calculated. So for the principal quantum number 1, we have only 1 orbital. And on this orbital, we will find 2 electrons that have different spins, okay? 1 up, 1 down, so 2 electrons. For the principal quantum number 2, so in fact, we will have 4 subshells, and on each of these subshells, we will have a certain number of electrons. So in fact, in this shell corresponding to n equal 2, we will have 8 electrons, and so on. So it is calculated according to the rules that we have described. Okay, so here you can see a more complex representation considering these subshells. Here it is for the sodium atom. And so it is a representation showing, for example, that the shell corresponding to n equal 2 have two subshells, S and P, and so we have the electron and subshells. But now it will be much more convenient to represent either as it is represented on the right figure on this slide, so showing the energy increasing and showing the different shells and subshells that have different energies and the electron placed on the subshells, okay? Knowing that in the case of the 2p subshell, we will have three orientations. So these three levels you can see correspond to the orientation 2p x, 2py, and 2pz. And on each of these orbital orientation or energy state, so we have two electrons with two different spin moments, okay? So this representation is given considering the atomic number for the sodium. So the sodium have, in fact, 12, no, sorry, it has 11 electrons, and so we place the electron from they are placed from the lower energy level, and they will fill the different shells and subshells according to the number of electrons that we have, okay? And this is according to the Pauli exclusion principle, okay? And we will also be able to represent the electron configuration in that way. So you can see here it is describes the different quantum number more precisely for the different electrons that will be found in this atom. Okay, so let's shift to the other slide. So we introduce the four quantum numbers. We have the Pauli exclusion principle, so that describes in which manner these states are filled with electrons. So we say from the lower energy state, and we are going to fill the shells and subshells in our atoms. And each electron state will hold only two electrons that will have opposite spin. So I think it is quite clear. We already talked about that. And we will give some definitions. So the ground state corresponds to, for an atom, correspond to the configuration where the electrons occupy the lowest possible energy. So as represented right here, we saw that first if it's 1s, 2s, 2p, when all the 2p subshells are filled, so 3s and so on. And in that configuration, we say the atom is on the ground state. So the electron configuration of an atom is a manner in which the states are occupied. And another way to write this electron configuration, instead of representing this graphic with increasing energy, we will also use this way of writing. So 1s2, 2s2, 2p6, 3s1. So you can see that 1 corresponds to the first quantum number, n, s corresponds to the subshell, and the subscript corresponds to the number of electrons placed on this subshell. So we saw that the s subshell will be filled with maximum 2 electrons, the p with 6 electrons, and so in that way, I represent how is the electron configuration from the sodium atom, okay? Then we can define the valence electron. What is the valence, or what are the valence electrons? They are the electrons that occupy the outermost filled shell, and they will be very important in our class. We are going to see that. And the stable electronic configuration is a state within the valence electron shell are completely filled. Okay, so the last shell of the atom possesses all the electrons permitting to fill this shell. So we find some atoms that fulfill these conditions, that have a stable electronic configuration. And in fact, they are called the noble gases. So here is the example for argon. So you can see that in the case of argon, the three shell, n equals 3, is totally filled. So the subshell S is totally filled, and the subshell P is totally filled also. So we say it has a stable electron configuration. And it is very interesting because in that case, the atoms that fulfill this condition are very stable. So they won't be reactive, they won't react chemically, okay? So why we are talking about valence electron and stable electron configuration? Because in fact, valence electron will participate in the bonding between atoms. So we are going to focus on the number of valence electron in our atoms. And many physical and chemical properties of material will be explained, will involve the valence electrons. So we introduced the electron configuration, and now we should introduce the periodic table that I'm sure that you know. So the elements are classified according to electron configuration. We have these representations that have been made in order to classify these elements according to the similarities that they present in their electron configuration, in order to understand some of properties such as electronegativity. So when you have a look to this periodic table, so you see that we have 7 rows in these periodic tables, or 7 periods, and we feel they are filled along the row by the number of shells that they have in their electron configuration, and along the row they are filled with organized considering the number of electrons that they have. And having a look to the different columns that are found in the periodic table. So we can start from the right column, the blue one. So the blue one corresponds to the rare gases, or that are atoms that have a stable electron configuration that we introduced. And so they are, as we said, very stable and stable chemically, okay? So on the 16 and 17 columns, we have the atoms that are lacking 1 or 2 electrons to get a stable electron configuration. And on the column 17, we have the halogens. So if we have a look to the electron configuration of chloride, that have an atomic number of 17, so you can see chlorine is missing or is deficient by 1 electron on the 3p5 on the valence shell. So then we have on the extreme left, on the 2 first column, we have first column is the alkali, second column are the alkaline earth metals, and they have either 1 or 2 electrons in excess that they will be willing to give in order to have a stable electron configuration. So let's take the example of sodium. So we saw that sodium has this electron configuration, and as you can see on the outer shell, it has only 1 electron on the 3s1, 3s, and so it is missing 1 electron, or it can give this electron to have a stable electron configuration that would be 1s2, 2s2, 2p6. Okay, so it will be willing to give an electron. Okay, and then we have all this block from the third column up to the 12th column that correspond to the transition metals. And the transition metals are partially filled d electron states. And this will be important for us to understand the chemical bonds found in metals. Okay, so we introduce a periodic table, and let's remember that we can distinguish some blocks. So we have the S block, P block, D block according to the outer shell that is found in this specific atom. So in the S block, the outer shell will be the S subshell. In the P block, it will be a P subshell, and in the D block, a D subshell, and so on. Okay. So let's introduce electronegativity. So in this periodic table, we can see a tendency for the electronegativity. So what is the electronegativity? It measures the tendency of an element to attract electron in a covalent bond. So a covalent bond, which means sharing electron between two atoms. So in this covalent bond, will the atom be more able to attract and to gain electron, or will it be more able to give an electron? So when an atom is more, its tendency is to give electrons, we say it is more electropositive. So if it gives an electron there, it will be similar more as a cation. Okay, so it will give an electron and it will be more positively charged. So we say it is more electropositive. And on the contrary, on the right of this table, on the upper right, we will have more electronegative atoms that will have a higher facility to gain electron. Okay, so like they would gain electron and they would be more similar as anion. And so we have an increase of the electronegativity on that evolved in that way in the periodic table. And this is explained by the fact that so the more electron that so it is related to the fact that it has an outer shell that has an excess of electron, or that have deficient of electrons. Okay, so we explained it. It will be more able to give an electron or to gain an electron, as we explained. And we explained that it is increasing through the periodic table because of the fact that on this part of the periodic table, we will have a lot of electron in the atoms. And so since we will have a lot of electron filling the shells, and specifically the shells that are more closer to the nucleus that is positively charged, you can imagine that going on the outmost shells, so these electrons, the attraction from the nucleus is shielded by the other electrons that are present on the lower energy orbitals or shells. Okay, and due to this fact, because this attraction is shielded, so they are more able to shift and be given to another atoms. So that's why in this region we have more electropositive atoms. And so when the number of electron is decreasing in in our atoms, or the number of protons is decreasing in the atom, so it becomes more electronegative. It feels more the attraction from the nucleus. Okay. To be more precise, there are measurements that are done in order to determine the electronegativity of each atom according to the atomic number, which is shown in this graphic. Okay, so we see that it's not a linear dependency of the electronegativity and the atomic number, but we can find the specific value in the literature. Okay, so now we are going to remember the types of chemical bonds that are found in materials. So first, let's define what is a chemical bond. So it is a union between atoms, and a chemical bond forms between these atoms if the resulting arrangement of its two nuclei and its electron in a lower energy state than the total energy of the separated atoms. So if we have, wonder which electrons are involved in the primary chemical bonds, so I think it's quite clear from the descriptions that we made from the electron configuration of the atoms and what is the more stable electron configuration. We say that it involves the valence electrons that are going to be given or to be gained by the atom. So it is given to the neighbor atom, or it is a gain from the neighbor atom, and it creates this chemical bond. So do you know some kinds of primary chemical bonds? I'm sure that you remember some of them. So we have ionic, covalent, metallic chemical bond, and it will depend, in fact, on the electronic structure of the atoms that compose the material. Okay, and we are going to distinguish primary and secondary bonds. So the primary bonds are called the chemical bonds, and the secondary bonds are called physical bonds. They are weaker than the primary bonds. We are going to remember it. Okay, so let's start first with the ionic bonding. So in ionic bonding, it will involve, in fact, the transfer of electrons from one atom to another. So do you remember the electron configuration of sodium and the electron configuration of chloride? We said that, in fact, sodium is willing to give a valence electron in order to be in its in stable electron states, whereas chloride is more willing to win one electron. Okay, so what is occurring is an electron transfer from sodium to chloride, and so as you can see, sodium turns to be a cation, whereas chloride turns to be an ion. Okay, and in that way, both of them are in a stable configurations, stable electron configuration, sorry. And so in that way, due to this transfer of electrons that is performed, since it is non-directional, in fact, the magnitude of the bond is equal in all directions around the ions. Okay, so it is the same in all the directions. So this magnitude, this strength of this bond is measured in Coulomb. Okay, and this kind of ionic bonding will occur when we will find a high electronegativity difference between the elements. So if we have a look on the tables, we will find that the electronegativity for sodium is 0.9, whereas the electronegativity of chloride is 3.0. And so you can see that the difference of electronegativity is 2.1. So in that case, we will describe that it has an ionic character. Okay, so so due to the fact that they have a high electronegativity, or I can say they are placed in very different position and columns that we already introduced in the periodic table. So one is able to give electrons, the other is able to receive electrons. Okay, and so the ionic bond is due to electrostatic attraction or coulombic attraction between two ions of different electrical charge. One that we will have formed a cation and an ion, so they are attracted by coulombic charge. Okay, and so due to this attraction by electric charge, we have what we call ionic bonding that is created. Okay, it is as a characteristic of ionic bonding. So and this coulombic force is changed with the squares of the inverse of the interatomic distances. So this will be important for the following of the class. So basically, we will find this kind of ionic bonding in compounds that are composed of both metallic and non-metallic elements. Okay, due to their electronic configuration and the high electronegativity difference between these elements. So now let's introduce covalent bonding. So covalent bonding involves the sharing of electrons between adjacent atoms. So it is the case, for example, between carbon and carbon and hydrogens, or also in this case between silicium and oxygen. We will have this kind of covalent bonding. So covalent bonding is directional because there is this sharing of electron in one specific direction between the two atoms. And it exists only in the direction between the two atoms. So in the direction of the closest distance between one atom and another, okay? So we will say that we have either highly covalent character for this covalent bond or ionic covalent character. So this will be calculated according to the difference of electronegativity of these two atoms. So for example, in the case of carbon and hydrogen, the difference of electronegativity is relatively low. So it has a highly covalent character, whereas the difference of electronegativity between silicium and oxygen is higher. So we will say it has an ionic covalent character. So in that case, you can see that the difference of electronegativity that is encountered in covalent bonding between the two atoms is lower than between the two atoms that form ionic bondings. Okay, so this is a characteristic, and it is found in compounds that are composed of non-metallic elements found more on the right side of the periodic table. So covalent bonding, so considering the molecular orbital model, a bond is formed by the interpenetration of a half-filled orbital of atom A with a half-filled orbital of atom B. So for example, in the case of hydrogen, you have one atom that have one electron, the others that have one electron, and so they will share their electron. One will have, so we will have to create, to get this interpenetration of this orbital, they will have to have opposite spins, and so they will be able to share these electrons and to create a covalent bond between them. Okay, so in a more complex situation or more complex shape of these subshells, in the case of halogen molecules. So you can see the shape of the D subshells that is filled with the valence electrons is more complex, and we have interpenetration of these two orbitals of these two molecules in order to share this electron and to create a covalent bond. So in covalent bonding, we will have to distinguish P and sigma bonds. So if the interpenetration of two atomic orbitals are on the same axis, we name this a sigma bond. So it is the case in that representation. So we have two P subshells or orbitals, and you can see that they are aligned in the same axis, and so they will interpenetrate in order to share their electron along this axis. And so we will call this the sigma bond. And we also find the p bonds that are the interpenetration of two atomic orbitals that are parallel. And so it is represented right here on the bottom of this figure. So you can see that we have these two p orbitals that are represented, and they are parallel one to another. So one in one atom, the other in another atom. And so by forming this, by sharing this electron thanks to the interpenetration of their orbitals, so they will share it on the two sides right here of these orbitals, and so we will name it the p bond. Okay, so the electron will be shared along this representation, which is vertical lines that are represented right here. Okay. So in order to explain the hybridization, we can take the example of carbon hybridization. So carbon has 6 electrons. And so first we fulfill the 1s subshell, and then the orbital 2s, and then 2p. So 1 electron on 2p x and 1 electron on 2p epsilon, as represented right here. So here you can see that we have 2 subshells that have a different energy level. And so we can have what we call degenerescence or hybridization of these orbitals in order to create a new kind of orbital, a hybrid orbital that has an intermediate energy between the initial orbital 2s and the orbital 2p. So as you can see right here. And so the 4 subshell will have the same energy. And in that way, you will have 1 electron on each subshell, and all of these electrons will have the same spin. And so in that way, we have a lower energy state of the valence electrons, and this valence electron will be shared with 4 other atoms. So in this hybridization sp3 of the carbon atoms, the carbon will form 4 covalent bonds. For example, in this case, it is representing methane. It is sharing this valence electron. So each valence electron will be shared with 1 atom of hydrogen that is willing to accept to share 1 electron with this carbon in order to fulfill this carbon shell. Okay, and this kind of hybridization is very important in polymers, as we will see. We will have such kind of covalent bond thanks to the sp3 hybridization that will be created for the carbon atom. So now let's explain the carbon hybridization sp2 after having introduced the sp3 hybridization. So in fact, we can have also another kind of combination of these orbitals. And as you can see, it will take such kind of combination of this orbital of different energy. And so when the carbon atom will be attached to 3 atoms, it will involve 3 sigma bonds and 1 p bond. And in that case, it requires to have 3 orbitals in a hybrid state. So it is the case if we compare the ground state of these carbon atoms and then the excited state that is represented in that way, the hybridized states in the 2p hybrids, we have 3 orbitals that are in a hybrid state at a higher energy than the 2s state, and one p orbital that won't be changed, okay, that will have the same energy that was predicted, okay? So it is an unhybridized p orbital. So in that way, in fact, we will have a kind of mix of the s orbital and p orbital that would be planned in the ground state, okay? So we have another orientation of these orbitals. And thanks to this geometry for this orbital, it can so organized, and we will have a specific direction for interpenetration of these orbitals, like represented in ethene. So in ethene, you can see we have 2 carbon atoms. In these 2 carbon atoms that are both sp2 hybridized, you can see that 4 CH bonds will be created that are represented with the red arrows in this representation. And they are made by the interaction of the sp2 of the carbon with the 1s orbital of hydrogen. And we will have also 1 carbon-carbon p bond that is made by the interaction of 1 sp2 of this carbon with the other sp2 orbital of the other carbon atoms. It is represented here in green. So we have these 2 orbitals that will cross each other to share this electron and to create this covalent bond. And we will have another bond that will be created by the interaction of this 2p orbital. So this 2p orbital is represented in dark blue and dark red. And so they will shift and interpenetrate together to create this p bond that we described before. So as you can see, depending on the kind of bond that we have and the kind of sharing of electrons that enable the lower energy state for the molecule created. So either we will find carbon in sp3 hybridization or sp2 hybridization, specifically for carbon, but we can also find other kind of atoms that suffer such kind of reorganization of their orbitals. So then we can introduce metallic bonding. So let's remember that metallic atoms possess 1, 2, 3 valence electrons. And in that case, they are willing to, they have this valence electron that will become to not be bound anymore to any particular atom in the solid. So the metallic bond that will be created between metallic elements will be non-directional, and in fact we will consider that we'll have the core of this atom that is represented right here, that has a positive charge. We call it the ion cores, okay? And between them we have these free electrons, these valence electrons that will be the free electrons, and it will create a kind of sea of electrons or cloud of electrons, and they will fluctuate around these ion cores, creating such kind of specific configuration. And so there is no repulsive electrostatic forces between ion cores, because in fact we have these free electrons that will create shielding between these ion cores. And so we will find this kind of metallic bond in metals and their alloys. And this free electron will be responsible for many properties found in metals, okay? And so let's remember that metallic bonds are non-directional, okay? And so we introduced the primary bonds. Now let's introduce the secondary bonds. They are called intermolecular interactions, or physical bonds, or van der Waals interactions. They are weaker than chemical bonds, the order of 10 kilojoule per mole, and it arises from atomic or molecular dipoles due to charge asymmetry. So we will consider that in our atom or molecule, we will have a part that is more positively charged and another part more negatively charged. So we have this charge asymmetry, and they will interact with each other. So one atomic or molecular dipole will interact with another one, and this will create an electric dipole due to this interaction. So we have this separation of this portion, more positively charged, more negatively charged. So it can be between permanent dipoles, so molecules that is permanently with this charge asymmetry. So two of these kind of molecule, permanent dipoles, or a permanent dipole or induced dipole. This dipole is created by the approximation of a permanent dipole, so it will influence the repartition of charge in these atoms or molecule, or two induced dipole due to the proximity of these two entities, so it will create this asymmetry of charges. So we have different kind of such secondary bonds that can be formed that have different energies. So ranking the energy of these secondary bonds, we have the energy bond, hydrogen bonds that are more energetic, stronger, then ion dipole, 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 induced dipole, induced dipole, induced dipole, okay? So this pair of kind of dipoles. So we can have a closer look and explain better what is the difference between an induced dipole bond and a permanent dipole. So in a permanent dipole, which is easier to explain, we will have constantly, permanently, a region with a more positive charge and a region with a more negative charge, which is the case, for example, in the molecule of hydrogen chloride. So the hydrogen has one electron that it is willing to give to respect to find the stable electron configuration, whereas a chloride is willing to gain this electron to be in a stable electron configuration. Okay, so gaining this electron, chloride become negatively charged, and giving this electron, hydrogen become positively charged. And so you have an asymmetric arrangement of negative and positively charged in this molecule. So it is a permanent dipole. The difference with induced dipole is that we have a permanent dipole, which is polar, which means one region is more electropositive, which is the region A, and another region is more electronegative, the region B, and it's coming close to a nonpolar symmetric atom. Okay, electrically symmetric atoms. And so the polarity and the dipole of the first molecule will influence will create a distortion of the charge in this second atom. And you can see that you can see on this representation that the negative part of the permanent dipole will repel the electron, so that will be distorted, and that will go in a region a bit more far away from this negative region of the permanent dipole, and it results in the induction of this dipole due to the repulsion of the charges, the distortion of the electric charge in this molecule. Okay, so we say that we have an induced dipole created by the proximity of the other one. So let's have a look to hydrogen bonds. Hydrogen bonds are a special case of a bond between polar molecules, and they are the strongest secondary bond. So their energy is about 50 kilojoule per mole, and it occurs between molecules in which hydrogen is covalently bonded either to fluoride, to oxygen, to nitrogen. And so the fluoride, oxygen, nitrogen have a pair of lone electrons. And so we will have here this hydrogen, okay, that will create a bond with this fluoride or oxygen or nitrogen that have a pair of lone electrons. And so it will result in such kind of bonding. Here you have a nice representation between the hydrogen of the second molecule of hydrogen fluoride that is interacted with the lone electron, the pair of lone electron of the fluoride of this other molecule, okay? And this kind of secondary bond are, as we said, quite strong, so it will influence in many properties, particularly in polymers. So to summarize, here we have a table that indicates the bonding energies that we find depending on the ionic, covalent, metallic, van der Waals, hydrogen bonds that we introduced. So for this, we find this kind of bond in the substance. So some example of this substance in which we find such kind of bonds. The value for this bonding energy. So you can see that the van der Waals secondary bonds have the lower energy, so it is more easy to break. Then we have the hydrogen bonds. Then we have, depending on the kind of molecules that we have, but covalent, metallic, and the strongest one are the ionic bond. And so, as you can see on this table, it seems that there is a relationship between the bonding energies and the melting temperature. So as you can see, it seems that just looking to this information, that the lower the bonding energy and the lower the melting temperature. So we already observe that there is a relationship between the thermal property and the kind of bond that we find in this material related to electronic configuration of the atoms that compose these materials. So now let's talk about bonding energy.